All right, thanks everyone for coming. And I'm Kitty. A little bit about myself. I work at Microsoft in the quantum systems team. So quantum education and producing materials and content to teach the public and our customers is part of my day job. But I also have a passion for art. So I'm kind of trying to learn to combine science and technology with art together. So I have a background in condensed matter physics. So I did my PhD in applied physics in Harvard, and before that I was in University of Cambridge. Started with low temperature experiments, trying to study the quantum phenomena of materials. And I moved more and more towards applications and worked at Intel and then Microsoft, a lot of entrepreneurship and silicon photonics. So now I'm back in quantum. That's kind of where I started. So it's very exciting that this industry is emerging, and there's a lot interesting information out there. And quantum computing is a subject that involves a lot of different areas. There's math and physics. There's also software and hardware. So I hope that this class will background and have some pointers to start digging deeper into the subject. So we're not gonna do it in the crammed way. We're gonna have a soft landing. So it will be pretty short every week. We're gonna have 30 minutes to discuss a concept. So that also can include theory. There's also hardware aspects I will show people, and there's also programming that I can lead people to the places they can learn how they can start coding and programming on a quantum computer. So I have a project on Hackaday, and thanks Hackaday for hosting this virtual class. It's called Introduction to Quantum Computing, and it has a summary of this project. I started using comics to explain the concepts. Every Wednesday and Sunday, I would post an update, and information about the class will also be posted there. So you can follow there to look at what topic will be discussed for the week. It will help if you have seen this before we start this 30-minute discussion. And throughout the week, feel free to post comments, post questions, and discuss with your peers on the Hackaday project. And I want to make this very interactive, so it's not just me teaching. I'm also learning, so I would love to discuss with you online or offline, and we can learn together. And I would highly recommend that you take notes for some of the materials that we show here, even though this is recorded. I want to encourage this reinforcement learning for natural intelligence, which means there will be materials that you will recall constantly. We may have covered some content a few days before, and now we are looking at it again from a different angle, and that will also provide me feedback. So feel free to ask questions during this class. And if you like to type your questions in the chat, feel free to do that. Sophie is monitoring. And you can also unmute yourself to ask the questions as we discuss. And if there's anything that is confusing, in any way, just ask, just raise the question. I cannot see you right now that I'm sharing my screen, but Sophie is monitoring the chat, and she can let me know if you are asking questions there, and I can try to explain that in a different way. So let's just take a few steps back to look at how computing has been developed to where we are, and right now is a perfect timing to start learning about quantum computing. So we are all very familiar with the technologies that rely on computing is pretty much everywhere. So all of our world functions rely on connectivity and technologies, and all of our problems we represent it on a computer, and we send it online through the data centers, and that could connect to some other part of the world. But there are still some problems that our most powerful computers still run into limitations. Even our supercomputers and high performance computing clusters are not capable of solving some of the most challenging problems. Those problems include a lot of things that relies on the fundamental behaviors of nature. Things like chemical simulations or discovery of new materials. Those fundamentally are quantum mechanical. That's the interactions between molecules and fundamental particles that are so small and they work in a quantum mechanical way. Our classical computers may run into limitations when we're trying to capture the behaviors of those systems. And there are also problems such as logistics or signal processing or security that fundamentally they're classical, but with our advancement in quantum algorithms, they can also help solve some problems in those areas, even though they may not be themselves quantum mechanical. So I would later on dive into more of the specific applications. And also we have at Microsoft developed a lot of libraries that that provide solutions to some of these industries. There are blogs you can read over there, and there are also code samples that you can download and try running those examples yourself on your own computer. So generally speaking, there are several application areas. So quantum simulation to me is the most interesting area because my background is in physics and our classical computers are not able to simulate all of the quantum systems. So if we can have a computer that is itself quantum mechanical, then they can be able to simulate the quantum systems. And then there are algorithms. There are quite a few algorithms that's developed since the 80s that can lead to very exciting applications. And there is also cryptography that quantum computer can bring solutions to. Most of the modern cryptography relies on RSA, which is factorization of huge numbers that could take unreasonably long time for a supercomputer to figure out. But then if quantum algorithm comes in, it can break the current RSA method, which is terrible. A lot of banks and governments are looking into that in order to prevent such criminal act. But at the same time, if we can have a quantum computer generating new types of cryptography methods, that's even better. I would say that quantum computer is like the other biomimicking tools. So obviously these pictures here I show are kind of easy to see that we were inspired by animals to build tools. But then we can also be inspired by nature, the most small building blocks of nature to build computers. So this course will start looking into the fundamental basics of how quantum computing works. And I would not overload you with information. So that's why we only have 30 minutes and would just talk about one topic per week. And throughout the week, you can let me know what you want me to draw, and you can look at the comics to see what's coming up next. So quantum computers could help us solve some of the problems that current computers cannot do efficiently. But what is it? On a high level, it is based on the laws of quantum mechanics. It's a computation based on that. It has a relatively pretty short history. It developed really, really fast. So it's really, yes.
Sorry.
Yep.
Are you sharing your screen anymore?
I am.
It's not showing up anymore.
Were people able to see the...
Go back a slide or two. It was sharing and now it's not. So we can see you, but not the screen.
Oh, okay. Let's see how many slides people have missed. Let me share again. So were people able to see the beginning?
We could see now.
Yeah. Did people miss the slides at the beginning?
Go, just click through them.
Yeah, I missed the slides, all of them.
Oh, sorry about that. I think it wasn't
okay.
functioning. So then I will just quickly walk through this. Yeah, I show people these. Are people seeing this dialogue? These.
Yes, the class structure. Yeah.
How about the thing I'm dragging my mouse? No. Okay. At least Zoom is hiding the video that I'm seeing myself. Okay. So I showed a few things here. The introduction to quantum computing project on Hackaday. So make sure that you check that out. And every Wednesday and Sunday, I'm posting a comic to a new concept, and then people can see what's coming up for this class. And here are two links that people can go to. One is to Microsoft's Q# documentation. That's actually an open source. So actually all of the Microsoft software development is open source, so you can even contribute. So Q# is the language that's used to code for quantum computers. And katas is a set of exercises you can walk through to learn how to do programming. So these two links are great, and they can lead to other materials and resources. So if you are interested, you should contribute. And then, yeah, I already mentioned that you should take notes and also post comments on the Hackaday page. So this is what I asked everyone to do, ask questions. You should have interrupted me earlier, but thank you for letting me know it wasn't recording. And if there's anything confusing, just let me explain the different ways. So I don't know how many people have already seen this pages, so I'm passing these through quickly. You can find them on Hackaday and my Twitter and LinkedIn and Instagram if you want to use those platforms. So I was talking about these applications that these are not the only applications that could be limiting the most powerful classical computers. There are more, but this is generally showing you that they're kind of both fundamentally quantum mechanical systems and also classical problems that could utilize quantum solutions to help. And I think we were here when we realized it wasn't sharing. So I wanted to show people that these pictures where we get a lot of inspirations from nature, and quantum computing is also one of those. So here is what I wanted to show, that it has a history since the 80s when it was first proposed by Mann and Feynman that we could create some machines that's based on the laws of quantum mechanics, and that could help us build simulation tools to mimic quantum mechanical systems. And then from there, we had quite a few algorithms developed, and they are all based on each other. So there were the first proposed quantum Turing machine by David Deutsch, and then Peter Shor came up with an algorithm for factoring. And Groover then produced an algorithm for quantum search. And there were more, and most of the later algorithms relate to some of these existing ones. And those algorithms could be limiting themselves, but then they show that they could solve certain problems that's more efficient than classical computers, classical algorithms. And then since then, we all know that in the past couple of years, all these big companies have jumped onto the subject. So Google, IBM, Microsoft, Intel are all working on, and a lot more big companies and startups working on both the hardware and software development of this. So we are in a very exciting time that this emerging technology is growing into an industry. So, and it's also a perfect time for us to get into it before it's too late, to really try to demystify a lot of the things that we hear all the time from media. So we know that our classical computing is based on the binary systems, and the modern computers are made of transistors to represent zeros and ones. Quantum computers are fundamentally different. So classically, we can describe a system using bits, and note this definition of states is you can imagine it as a status or condition of your system. So say if your light is on or off, then you can represent it as 0 or 1, or 1 or 0. Say your temperature is too high or too low, that could also be represented as 1 or 0. Or if you flip a coin, the head and the tail could be 1 or 0. So all these metaphors that I chose are like conveniently binary. And mathematically, we can also just write it out as vectors. So 0 is in the two-dimensional space, and there are only two possible ways to represent the classical bits 0 and 1. So 0 we can just write 1 0 and 1 as 0 1. There are only these two possibilities for a basis of 2. And if you have more classical bits, you can just write it out as a combination of 2 bits. And the mathematics that's used here is called a tensor product. I've written out here how tensor product works. This is basically how you put 2 vectors together and then try to calculate the result of their tensor product. So the first one times these 2, the second one times these 2. So you can walk through the math later. That's not critical right now. But using vector would make the representation very easy later on as we get more into it. But simply looking at this, you can also see that if we have 2 qubits, then that's 4 possible configurations, 4 possible ways to represent the 2 bits. 0 0 0 1 1 0 1 1. There's no other possibilities. It turns out you can write it out. If you do the maths, you get this 1×4 vector. But even without doing this tensor product, you can see these are the 4 possible ways to arrange the numbers. 0, 0, you will have the 1 starting at the first element. And the second one will have the 1 here. The third one will have the 1 third. Fourth one will have 1 at the bottom. So that's a 4-dimensional, it's called Hilbert space. But don't worry about these terms. We'll just get more intuition. And we know that classical computers are built on transistors that would represent 0 and 1. And how transistors work, I won't go into details, but it's basically a semiconductor sandwich. You can have the electrons to go through your material or not based on the voltage you apply to the material. If you let, say, let the voltage or electricity go through, you can say that is 1. If you don't let it go through, you label it as 0. So that's how bits, classical bits, are physically made in computers. So I'm using quite a lot of analogies here, and quantum computing is a more correct way to describe nature, I would say. So it functions completely differently from this binary way of representing information. So a switch-like binary building block is 0 and 1 is a much more simplified version of how nature behaves. Nature, which is made of the fundamental particles and the quantum mechanical particles like electrons, photons, atoms, etc. They have energy states. So everything is built on top of these things. So at the very low level, they have the energy states that are in superposition. So it's not 0 or 1, but different states in a coexisting manner. So I'm gonna explain a bit about what superposition is, and that is the fundamental behavior for a quantum computer. So classical bits, again, you have 0 and 1 that you can make all kinds of metaphors to say that. So if I have a circle, if it's empty, we can label it as 0. If it's filled, it is a 1. For a quantum bit, shorthand qubit, it can represent 0 and 1 in a single qubit. So here you can say we have 1/3 of the state 0 and 2/3 of 1 in it. Another metaphor you can say, we have some lottery thing, and if we have 20 balls, if they're all red, they're 0, or blue, they're 1. But then if you mix it up, we can have arbitrary numbers here. So say 8/20 is 0 and 12/20 is 1. You can change any number here. And then a coin, you can also say a head is 0, a tail is 1. If it's an even coin, if you rotate it, you know that there's 50% chance of landing on 0 and 50% of landing on 1. So you see that here, the quantum bits, qubits, is related to the probabilities of the amount of information in there. So a spinning coin is a metaphor for head and tail in superposition. Again, representing it mathematically, I hope you made notes earlier to write down what 0 and 1s are. So a state, a state for a qubit, we can again represent with a vector. But now instead of just 0s and 1s in the vector, we can have amplitudes. we can have any number A or B. If you split it up, you will see that is A amount of 0 plus B amount of 1. So that is to say that a quantum qubit is a state that is a superposition between 0 and 1. And or another term is linear combination of these two possible states. And they each has a weight in front of them. So A and B tells you how much of 0 and 1 is in your whole system. The only requirement for them is that their amplitudes squared sum to 1. What does that mean? So in our earlier example, a circle with 1/3 of 0 and 2/3 of 3 is basically saying that the probability of finding the circle in 0 is 1/3. The probability of finding the circle in the black one is 2/3. So A squared and B squared are probabilities of how much of those possible outcomes you can get. So similarly with the other two metaphors, you can write it out. So common sense, when we have a complete system, all of the possible probabilities will add up to 1. So there's nothing more to that. This is called a normalization condition. So this is a simple way to represent a qubit. It is a linear combination of two possible states. If you have multiple qubits, you can do the same thing like before to have a tensor product between different qubits. So if you have 2 qubits, you do this tensor product again, you get 4 different amplitudes. And again, the amplitudes are the coefficients to tell you how much of these 4 possible states, 4 possible configurations that's in your system. And you get the probabilities of each, add them up, they should be 1. That's the only requirement for this to work. So that is a qubit. That is different from a classical bit that is just 0 and 1. A qubit is a state with superposition of all the possibilities. And I think I will stop here for today. We'll talk a bit more of the significance of this, why we use superposition, and what does this lead to, and give you a bit more intuition of the concepts later on. Hope this helps. Let's see, if anyone has questions, feel free to ask.
There's a few questions. Hi, Kitty. That was amazing. Really enjoyed your slides. There are a few questions in the chat, and I think people should interact with you. But one thing that a lot of people, or a couple people have said, will you be giving access to the slides?
Yeah, I should. I think we can share the recording. And I'm kind of building the slides. I don't know if it's better to keep adding. I guess I can just update the slide on the Hackaday project.
Okay. Can you see the questions, or do you want me to read them?
I just opened up the chat. Let me first post the link to the Hackaday project so people know where to find the materials.
Yeah, I can do that for you.
Okay, great. Thank you. Okay, some questions. Should I start from the beginning?
I moved them all kind of down close to the end.
Okay. Go backwards.
At 2:52. Or whatever that time is for you.
I have 8:52. Okay, question 1 so far. Why do we need good hardware for 3D simulations? I don't know how to answer that because we're not talking about 3D simulations here. So I'm not an expert in 3D simulations.
Okay. Burke answered that question a little bit further down. So start with question 2.
Is quantum computing useful for modeling protein folding? Possibly, yes. There are a lot of chemical and biological problems that's beyond what classical computers can do. So that's definitely an area of interest. And there's a lot of pharmaceutical applications, fertilizers for architecture. So that's relying on the chemicals and biomaterials that could be useful. 3, can you suggest resources for quantum computing hardware? For hardware, so there are, as I mentioned earlier, there are quite a few hardware big companies that are building hardware and startups doing that. I think it's hard to say resources unless you join those companies and work in those teams to work on those hands-on. If you just want to read about them, all these companies produce their blogs. Microsoft does a good job writing about the recent developments of our hardware. We actually just published a paper. So I would also share with you later on in our classes more about hardware, how different hardware systems work. There are many different kinds of quantum computers. There are many different approaches. So I will show you in the next few classes and make cartoons for those too. I can explain the first, okay. Will we get access to the slides? Yeah, so I would love to know people's background here too, if, in terms of percentage, material scientists, hardware engineers, software engineers. We'll probably have a good mixture. And this topic is definitely interesting for a lot of different areas. So we're gonna talk about different aspects. Just don't want to overload you with information and burn myself out. In rendering imaging, then you would draw a complex shape. First, you would draw. Oh, okay. That's the answer to 3D simulation. Thank you. There are softwares that one can use to reinforce one's understanding. Yes, so the 2 links that I shared earlier, the Q-Sharp documentation is open source documentation we produce. By the way, I manage that page, the Microsoft Q-Sharp documentation, and would love your contribution to that. It's a good place for you to learn about the Quantum Development Kit, QDK, and how you can write samples and programs in the Q-Sharp language. So you can walk through those examples and walk through the documentations there. And there's also the quantum katas, the link I shared in the slide, where you can walk through exercise questions using high-level languages to represent your quantum algorithm and be able to run your code in a quantum mechanical way. So please, could you mention a bit about deep learning algorithm? Okay, so this is something that I'm still learning too. We just published a documentation on quantum machine learning. So using the quantum is a complex circuit structure to represent neural networks. So I can show you in later classes, and I need to get a bit more hands-on with that, and then I can share. But if you want to jumpstart, just go to the quantum documentation on Microsoft's page and try run the QML, quantum machine learning algorithm. Any open source hardware? Not that I know of. I think the ones that I know are all closed source, unfortunately, but it's also very difficult to make it open source. So a lot of the system that I would show later, they rely on cooling things down to extremely low temperature. So as low as possible, but then there are systems that do not require as low, but still you have to merge it into liquid nitrogen and hydrogen and helium and cool it down to a few hundred millikelvin. So that's pretty difficult to do in your own garage, but I don't know, there could be ways to open source parts of it, like having people run things on them through the cloud. But a lot of software developments are open source, but hardware is not the same way as we understand it in the hacker community. So what languages will we write code in, if any? That would be Q#, is like C#, but is quantum sharp. So we would try some examples later. Do you have any recent estimation about how far we are from manufacturable? Depends on the hardware system. They're already manufacturable, just means how ready they are to run certain problems. So we can go a little deeper on. I see a lot of interest in hardware, so I would have some dedicated time for hardware. Any reading recommendations beyond applied? That's a good one, and applied approach. Or quantum computing for software engineers interested in hardware designs and deeper mathematical quantum computer algorithms, circuit design. Okay, not without depth. Relocated, co-located. Oh, co-located for advanced readers. Yeah, so I think one of the reasons that we are we're hosting a class here is that sometimes we don't find the exact right materials to self-educate. That's what I feel when I started learning this. So even with a physics background, it doesn't mean that I know about quantum computing. So I had to self-teach. About 2 years ago, I started doing this and then found a lot of media articles. They never explain anything. And then if you want to get deeper, it's all textbooks. And you have to have a physics background to really sit down and read through those. So I think that we need things in between. That's what I'm also trying to do to bridge the gap. So there will be more materials coming out. So if you want to see the most cutting edge, definitely use those companies' website that they would blog and post new features. And we've been doing a pretty good job at Microsoft doing that. So I'm a little biased, you can follow the documentation page that I manage, and we would have more interesting materials. But the books that you mentioned here are pretty good, as I learned. But of course, we need more. There is Q# and also Python Quantum Kit. Yeah, thank you. Circ is Python oriented. Yeah, that's Google's. Q# is much better. Thank you. Qiskit is IBM. Yeah. There are tutorials for quantum circuits on NISQ devices. I haven't looked much into it, so yeah, you may be able to teach us. As people find more, I definitely want to make this a collaborative learning. So as people find more information, more materials that they recommend, please post them on Hackaday so we can all share and learn those. Sorry. Yeah, my room is a little echoey. I'm still waiting for my supplies to get better audio. Bear with me. Hopefully next week it will sound better. Do you like to add something on hardware with experiments? Yeah, I would add some. And I will also explain what's topological quantum computing, which is a very different way from the other type, like supercomputing, superconducting circuits, or called, what's it called, trap ions. So,
Wait, am I the only one here?
sorry?
Oh, never mind.
You can speak up, no problem. Yeah, you don't have to, you can jump in and talk.
Oh, no, I just saw everyone's thing, like, no image, so I thought.
Oh, okay. Yeah, we're just looking at the questions in the messaging. Oh, there's still 41 more messages. I don't know if we have time to go through all of these. Could I recommend we post the remaining questions so we answer them online? Okay. Yes. Represent quantum states with vectors mathematically, but could explain its physical significance. Yes, when we get into hardware, it will become obvious. So just a little, I know it's not enough, 30 minutes, but that's the amount of information I would like people to digest for the week. And then we can keep the other topics coming up. Okay, so I think we should pause.
Kitty, I'm going to post one more time the project link, and people can post their questions in the comments there.
Yeah, that's great. Thank you, everyone. It's very exciting to see all these great questions popping up. And it's definitely a good place for us to learn, so we can consolidate those questions to the same place, and we can help each other learn. And don't just rely on me to answer all of the questions. If anyone already knows the answers, please jump on it and help your peers. Yeah, great questions. Thank you, everyone. Okay.
Hi, Wo, and everybody else who wants to keep chat info, I'm gonna close this in about 3 minutes. If you want to keep the chat info, you need to copy and paste it into your own browser or somewhere.
Okay, I'm gonna
It won't save.
Thanks, everyone. I'm gonna jump off. Haven't had dinner.
Bye, Kitty. Thank you.